But of course now we can take advantage of new optical methods for measuring the isotope ratio of water vapor. And over the last 5 or 10 years, these methods have been developing rapidly, and we now have numerous sites, measurement locations across North America that are continuously measuring at very high frequency the isotope ratio of water vapor near the land surface on towers, or sometimes via campaigns collecting in aircraft. Okay? So this is now the preferred method, but the data sets are very young. Continuous data sets are only a few years old at this stage, and so we're just beginning to understand how to interpret the spatial and temporal patterns of water vapor in the atmosphere to test our ideas about how air masses are mixing, about the coupling and evapotranspiration recycling to the atmosphere. We're just now beginning to be able to look at that at a very fine resolution. Unfortunately, the temporal resolution is there, but we don't have the spatial resolution yet because not many people are doing these sorts of things. All right, and just some platforms for making these measurements. Up on the right-hand side, you'll see the tower, the flux tower that we use in Wyoming for measuring CO2 and water vapor exchanges, and we've recently installed a laser isotope system to measure continuously the water vapor isotopes in the profile of the vegetation and as well as above the vegetation to start characterizing the controls of advective moisture versus evaporated, transpired, and sublimated water off the land surface and how those interact. And there are other technologies that have developed. There are radiative sensors on satellites that can detect the signatures of deuterium in water vapor throughout the entire tropospheric layer, and that's been quite valuable for looking at high frequency and high spatial pattern, high density spatial patterns of moisture mixing and distribution across the globe. And I put a paper in your folder from Warden that describes some interesting applications there, but I'm not going to talk about it. Okay, so let's go back to week 1, probably day 2. You learned about the Rayleigh distillation model for the transport of water from the ocean to the land surface. And you learned that water vapor comes off the ocean, is advected onto the continent, and through a series of condensation events, the water vapor isotope composition of the air mass gets depleted in the heavy isotopes because the heavy isotopes preferentially condense out. And as that moisture advects across the land, the isotope ratio values of the subsequent precipitation get lower and lower. Well, that's a really simple idea and doesn't capture all the nuances, the important nuances that are involved here. This simple model doesn't show any effect of mixing of different air masses, for example, that can greatly alter this sort of simple conceptual idea. It also doesn't clearly show the effects of the isotope effects and the mass balance effects of evapotranspiration from the land surface back into the clouds. So ideally, this kind of simple model never really happens because of these other processes. And so because of that, we get some really interesting patterns of the isotope ratio of precipitation across the landscape that can reveal some of these other interesting nuances. And I'll talk about those. And also, just as to go backwards a little bit, you've seen this a million times. This is the dual isotope plot for hydrogen and oxygen and water. And you see the equilibrium line of 8 and the effect of evaporation into a dry air that causes an effect on the abundance of deuterium versus oxygen that lowers the slope of that relationship by some factor, depending on the dryness of the atmosphere. So this is a really important effect, this evaporation effect on the isotope signal of air masses as they're moving across the continent. Thus, we can use the offset, the deuterium excess value, as an indicator of evapotranspiration recycling to the atmosphere. Because if you look at the evaporate on the bottom left over there, the deuterium excess value is increased. In other words, the evaporation moving back into the atmosphere has a higher deuterium excess than what you find along the meteoric water line. And that mixes with the cloud masses such that the subsequent precipitation events are likely to carry an imprint of that recycling history. And we see this in regions across the globe. Particularly, there's some notable examples in the Great Lakes area of North America, in the Amazon basin, which have been the focus of a lot of attention looking at these effects, and particularly using isotope mass balance of air masses to characterize, using d-excess to characterize and quantify the amount of recycling that contributes to the mass, the vapor mass of a cloud or of an air mass moving across the continent. So we're looking for that deuterium excess effect and its influence on precipitation across continents. That's not the only process that can influence deuterium excess. If we look at the globe, the precipitation patterns of deuterium excess across the globe, we see some interesting continental scale patterns. Note that in the Mediterranean region, because of the warm air masses moving off continents, moving over the Mediterranean Sea, which is dry, you get a strong deuterium excess effect leading to precipitation in the regional area with high d-excess values. So that's not necessarily recycling from the land surface, that's evaporation off the Mediterranean Ocean leading to that d-excess effect. And you also notice in other locations, like on the American northeastern seaboard, where there seems to be high d-excess values, that's related probably to dry air that's advecting off the continent from west to east, mixing with North Atlantic Ocean air, and some of that moisture advecting back onto the land surface and carrying a distinctively high deuterium excess value. So those aren't continental recycling effects. Those are ocean land surface interaction and mixing effects that are leading to those patterns. But note over the Great Lakes area, from the precipitation d-excess values, there is a strong signal of evaporation recycling there. And then you can note in the Amazon basin, there's kind of a hint of continental evapotranspiration recycling contributing to a higher d-excess in those regions. Some areas have low d-excess values, probably because compared to the global average meteoric waterline, those areas are receiving moisture from oceanic areas with high humidity rather than 85%, which is the global average humidity across oceans. You see areas with really low d-excess values, meaning their moisture source is coming from really humid air masses coming off of oceans. So anyway, there are some hints of continental scale feedbacks on moisture budgets of atmospheric water vapor, and I'll show you examples from the Great Lakes areas and then from the Amazon, or vice versa, start with the Amazon. So this is a really old data set, but it first highlighted how you can use isotopes to characterize and potentially quantify evapotranspiration recycling and its influence on the moisture budget of continental air masses. And what it shows is the expected oxygen isotope composition with very simple Rayleigh distillation, which is the dashed line moving from about -2 per mil and downward as air moves from the Atlantic westward across the Amazon basin from right to left. So you'd expect, with no recycling of moisture from the land surface, that based on the mass balance of moisture in the air and precipitation, one would expect the precipitation across that gradient, that latitudinal gradient, so it's a longitudinal gradient, would follow that ideal Rayleigh curve. But the measured values show a different story. The measured values show a much shallower slope, suggesting that a lot of the water that falls in the Amazon basin moves right back into the atmosphere, oftentimes causing no change in the isotope ratio value for oxygen across that longitudinal gradient. And in fact, moisture is recycled multiple times as air masses move across the Amazon basin. And knowing that, and then also thinking about that earlier slide of land use change, anthropogenic land use change, you can imagine that with changes in evapotranspiration induced by human activities, that will have an important feedback on the climate system of a place like the Amazon, which is so dependent on recycled moisture. So these are things to pay attention to as we understand global change and the future of water resources and its effect on freshwater resources and runoff and groundwater recharge. So that's not deuterium excess. The next example comes from deuterium excess values or measurements. And what this shows is a paper by Gabe Bowen recently showing that the amount of rainfall coming or landing on the leeward side of Lake Michigan has a strong imprint of evaporation from the lakes. So this is a strong lake effect of the large lakes in the Midwest. So this map shows the amount of rainfall across different regions in the leeward side of the lake that come from recycled vapor off of the lake. So very, very strong lake effects. We see that a bit here in Salt Lake City as well. During the winter, there are strong lake effects where moisture is coming off the Great Lakes and adding to the snowpack in the wintertime across the Wasatch Front. This shows that in great detail. So on that side of Michigan, there's a lot of the surface water resources come from evaporation and recondensation of water off of Lake Michigan. And this was determined using a deuterium excess mass balance model. So it's a really nice paper to show how you can apply just DXS values to calculate and quantify the amount of recycled vapor in precipitation. And from the study, it was noted that about 10 to 20% of the water evaporated from Lake Michigan falls right back down as precipitation in the downwind drainage basin. So this is a very significant effect on the land surface precipitation. Okay, so just a quick set of summary notes from this first part, just to get you kind of warmed up about the atmospheric water budget and the coupling between the land surface and the atmosphere. Are there any questions at this stage? Yes, Jason.
With this DXS, let's talk a lot about evaporation rather than transpiration, even though we see a enrichment in the leaves. Mm-hmm. So are we not picking up that signal, or is it only in transpiration?
That's a really good point. And because all the water that comes in through the roots is going to leave through the leaf at some point, over more than a day or two, the water isotope ratio value of that pulled in by the roots is going to equal that moving off the surface of the trees. And so in the case of transpiration, there's likely not much of a de-excess effect of that. But plants are taking up water from the surface in soils that have evaporated and are picking up a de-excess signal that's being transferred to the atmosphere. But the de-excess effect really is coming from open bodies of water, pools of water, and from evaporating surfaces like during interception from canopies and from soil evaporation. So that's where the strong de-excess effects are occurring.
Tomorrow.
Jim.
I have a different kind of question.
Sure.
Sterling et al. Sort of describes where ET is today. Has anybody projected where ET will be in 50 years? Will we lose a good share of the rainforest? Because you were just talking about it.
Yeah. Well, in addition to that GIS modeling effort that could be used to make those projections, I don't know. I don't know if those simulations have been made. That's definitely worth looking into. And because of that note, if you invite me back next year, I'll comment on that. I know that's a washout, Jim. I totally understand. That's a really interesting idea. If land use changes are so important for controlling this ET recycling, one must be able then to simulate its effects on continental precipitation. Yeah, it's a strong effect. It's probably equal to the stomatal closure effect of CO2, so we need to pay attention to it. I haven't looked at the most recent literature to see if there are any simulations that look at that yet. We do have another talk later today. I'm going to have to move on. Yeah, I'm sorry I can't comment on some of these details. I really just wanted to show this as an example of how you can use just the DXS signal by itself to calculate and quantify this recycling effect. And that's kind of what this paper shows.